All right, the FGH40T120SMD is a high-power semiconductor device known as an IGBT, or insulated gate bipolar transistor. It's produced by Fairchild and is rated for 1200 volts and up to 80 amps of current. This particular model uses what's called field stop trench technology, which is a modern design that combines high efficiency, fast switching, and low energy loss. Devices like this are typically used in solar inverters, uninterruptible power supplies, welding equipment, and power factor correction circuits. At its core, the IGBT blends two worlds: the high input impedance control of a MOSFET and the powerful low loss current handling of a bipolar transistor. The trench structure refers to vertical gate channels etched into the silicon, which help reduce on-state voltage and improve switching speed. The field stop layer acts as an internal electric field barrier, allowing the device to block high voltages while keeping the silicon layer thin and efficient. The FGH40T20SMD can handle up to 1200 volts between its collector and emitter, and it can continuously carry 40 amps of current when its case is at 100 degrees Celsius. At room temperature, it can manage up to 80 amps. The gate-to-emitter voltage range is plus or minus 25 volts, meaning that's the safe control range for switching. Inside, there's also a built-in fast recovery diode, which is essential for inverter circuits where current flow reverses direction quickly. This diode conducts when the main transistor turns off, helping to reduce stress on the rest of the circuit and improve efficiency. When it's operating normally, the IGBT begins turning on at a gate voltage of about 5 to 7 volts, and when fully on, it drops only around 1.8 volts across the collector and emitter at 40 amps of current. That's quite efficient for such a high-power component. In switching terms, it's also quite fast. The total time it takes to turn on and off is on the order of a few hundred nanoseconds, and the total switching energy lost per cycle is only a few millijoules. The gate charge, which is the amount of electrical energy needed to drive the gate, is about 370 nanocoulombs, so you need a strong gate driver to operate it efficiently, especially at high frequencies. Because high-power devices produce heat, thermal performance is critical. This IGBT has a very low thermal resistance of about 0.27 degrees Celsius per watt from junction to case. In simple terms, that means for every watt of heat it generates, the chip's temperature rises less than 1/3 of a degree above the case. With proper heat sinking, it can safely handle several hundred watts of power. Physically, the FGH40T120SMD comes in a large TO247 package, a 3-pin bolt-mounted case designed for solid thermal contact with a heatsink. The back metal tab is connected to the collector, while the gate and emitter are the two front pins. In summary, this device is a robust, fast-switching, and efficient transistor that sits at the heart of many modern power conversion systems. Its design allows it to handle high voltage, high current, and high frequency operation, all while maintaining low losses and good thermal stability. Perfect. Let's continue in that same smooth, spoken tone. Imagine I'm guiding you through how this kind of transistor actually works inside, step by step. To understand what an IGBT really is, it helps to picture it as a bridge between two classic types of transistors. On one side, we have the MOSFET, a metal oxide semiconductor field effect transistor. It's controlled entirely by voltage on its gate, which means the input draws almost no current. MOSFETs are fast and easy to drive, but when you start handling hundreds or thousands of volts, their internal resistance gets large, and that means higher conduction losses. On the other side is the bipolar junction transistor, the BJT. It can carry a lot of current with low voltage drop, but it's controlled by current, not voltage, which makes it slower and harder to drive. The IGBT takes the best of both worlds. It uses a MOSFET-like gate to control a bipolar conduction path. Inside the silicon, there's a layer structure that does this clever trick. When you apply a positive voltage to the gate, usually around 15 volts, it forms a conductive channel under the gate's oxide layer, just like a MOSFET would. This allows electrons to flow into a region that triggers the underlying bipolar transistor. Once that happens, the main current, from collector to emitter, flows through the bulk of the device, carried by both electrons and holes, just like in a bipolar transistor. This mixed conduction is what gives the IGBT its low on-state voltage and high current handling ability. When you remove the gate voltage, the channel disappears and the bipolar part shuts off, but not instantly. The stored charge inside the silicon takes a little time to recombine, which creates a brief delay in turning off. That's why IGBTs generally switch a bit slower than MOSFETs, though still fast enough for most inverter and motor drive applications. The trench version of the IGBT, like the one in this datasheet, improves on older designs by digging vertical trenches into the silicon for the gate structure. This increases control over the current path, reduces resistance, and allows more current in a smaller chip. The field stop layer adds a built-in region near the collector that stops the electric field from spreading too far. That way, the device can block high voltages, up to 1200 volts in this case, without needing a thick, inefficient drift region. All of this together gives us a device that's efficient both in conduction and in switching. When it's fully on, the voltage drop is only a couple of volts, even at tens of amps of current. When it's off, it can stand up to a kilovolt or more without leaking more than a few microamps. And when switching, it can handle the fast voltage and current transients typical of inverter circuits. You can think of the IGBT as a power valve that opens and closes under the command of a gate voltage. Because the gate draws almost no current, it's easy to control. Yet the device itself can steer enormous amounts of power, tens of kilowatts if properly cooled. That's why it's used in places like solar inverters, electric vehicle drives, welding machines, and uninterruptible power supplies. And that's the essence of the IGBT, a hybrid device that merges the efficiency of a bipolar transistor with the ease and speed of a MOSFET. Would you like the next part to go deeper into how Let's go through it carefully, in clear and flowing language, so you get both the physical picture and the reason it matters. The meaning of FS trench technology. FS stands for field stop, and trench refers to the trench gate structure used in the transistor's silicon. So, field stop trench technology means the IGBT uses both a trench gate design and a field stop layer in its structure. These two features work together to improve the efficiency, switching speed, and voltage handling capability of the device. Let's look at them one by one. 1. The trench gate. Imagine slicing through the silicon vertically. In older planar IGBTs, the gate was laid flat on the surface of the chip, and the current had to flow sideways and then downward, not very compact. In a trench IGBT, engineers etch deep, narrow vertical trenches into the silicon and fill them with gate material, insulated from the surrounding semiconductor. This means the gate now sits on both sides of the current channel, vertically, controlling it more directly and more efficiently. Here's what that achieves. The channel density increases. More current can flow for the same chip area. The on-state voltage drop decreases because the current path is shorter and better controlled. The gate drive becomes more effective. A smaller gate voltage can modulate a larger current. So the trench design mainly improves conduction efficiency and current density, letting you build smaller, faster, and cooler devices for the same power rating. 2. The field stop layer. Now let's look deeper into the silicon, near the collector side. An IGBT must block thousands of volts when it's off. To do that, you need a drift region, a layer of lightly doped silicon that holds most of the electric field when the device is reverse biased. But in classic designs, this drift region had to be very thick to handle high voltages, and that thickness increased the on-state resistance and switching losses. The field stop layer solves that problem. It's a specially doped layer placed near the collector side that stops or absorbs the electric field before it spreads too far into the silicon. In other words, it acts like a built-in cushion that ends the voltage gradient gracefully inside the chip. Because of this field stop layer, the drift region can be made thinner without sacrificing blocking voltage. And that's huge. A thinner drift region means less stored charge, faster turnoff, and lower energy loss. Putting it together, why FS trench matters. When you combine a trench gate with a field stop layer, you get a transistor that conducts more current per unit area. switches faster because there's less stored charge, has lower voltage drop when on, and still blocks the same high voltage when off. This combination became the dominant structure for modern IGBTs because it balances three things that used to fight each other: high voltage, low conduction loss, and fast switching. The FGH40T120SMD you're studying is exactly such a device. Its field stop trench structure is what allows it to handle 1200 volts and 80 amps, yet still turn on and off in tens of nanoseconds with only a couple of volts of drop when conducting.
We will move on to the next section shortly, but before that, I want to share something that might be very useful for you. Inspired by successful YouTube creators making fortunes from their channels, then Tube Mastery and Monetization course from Matt Park can help you get real results on YouTube with personal attention from him and his content team. Lots of people have already succeeded with their channels thanks to him. He also has Tube Magic software tool that can help you accomplish more when it comes to making content. Links in the description. I've also prepared a video for you that talks more about that, as well as solutions to challenges like online security, financial progress, and additional creativity. There, we'll explore these topics with respect and care for you. I warmly invite you to watch this video when you get a chance. Either way, your support is the current that powers this channel. And now back to the show.
Excellent question, and a very important one, because the temperature coefficient, or TC, tells you how a device's behavior changes as it heats up. Let's go through it step by step in the same clear, spoken style tone. What temperature coefficient means? Every electronic component, whether it's a resistor, a diode, or a transistor, changes its electrical properties when its temperature changes. The temperature coefficient describes how strong that change is and in what direction it goes. In simple words, it tells us whether the device's main parameter, like resistance, voltage drop, or current, increases or decreases as the temperature rises. If the quantity increases with temperature, we call that a positive temperature coefficient. If it decreases with temperature, we call it a negative temperature coefficient. 2. Why it matters in IGBTs. For an IGBT like the FGH40T120SMD, the key quantity affected by temperature is its on-state voltage drop, written as VCE SAT, the voltage between collector and emitter when the transistor is fully on and carrying current. Now, here's the important point. In older bipolar transistors, as they got hotter, the voltage drop actually went down. That's a negative temperature coefficient. It caused a serious problem. When you put several devices in parallel, one would get slightly hotter, its voltage drop would fall, it would carry more current, and it would get even hotter, leading to thermal runaway and failure. Modern trench IGBTs, including this one, are designed to have a positive temperature coefficient in their conduction region. That means as the junction temperature increases, the on-state voltage rises slightly. In practical terms, when one device gets hotter, its voltage increases a little, so it naturally carries less current, while the cooler devices carry more. This self-balancing behavior makes parallel operation safe and stable. The devices share current evenly instead of competing with each other. Hash 3. The physical reason inside the IGBT, current flows through both MOS and bipolar paths. At low temperature, the bipolar component dominates, and that one tends to have a negative coefficient. As temperature rises, carrier mobility drops, resistance in the channel increases, and the voltage needed to maintain the same current goes up. This combination flips the overall sign of the temperature coefficient from negative to positive, especially at higher currents and modern field stop trench structures. 4. The takeaway. So when the datasheet says positive temperature coefficient, it's good news. It means the device is thermally stable in operation, easy to parallel with others, and less likely to suffer from runaway heating. You can think of it as a built-in safety feedback. Heat makes it conduct a little less, which cools it down again. Very good and often overlooked question. You're digging right into how datasheet specifications connect to real physical testing. Let's unpack it slowly and clearly. 1. Where the line comes from. In the FGH40T120SMD datasheet, one of the bullet points under features says, open quote, 100% of the parts tested for ILM 1. Close quote. That sentence refers to a specific parameter listed earlier in the absolute maximum ratings table. Open quote, ILM1, clamped inductive load current at T sub C sub equals 25 degrees Celsius equal 160 A, close quote. So ILM1 is that clamped inductive load current, and the note 1 means there's a footnote giving the test conditions. If we check that note in the datasheet, it says something like, open quote, VCC equals 600 volt, VG equals 15 volts, IC equals 160A, RG equals 10 ohms, inductive load, close quote. That's the setup used to test the device. Mark 2, what clamped inductive load means. When testing power transistors, engineers often use a clamped inductive load circuit. Here's the idea. An inductor is charged with current through the transistor, and when the transistor turns off, that inductor tries to keep the current flowing. It doesn't like sudden changes. If nothing stops it, the voltage across the transistor would shoot up and destroy it. So a clamp, usually a diode or a controlled voltage source, is placed across the transistor to limit how high the voltage can rise. This setup safely tests how much current the transistor can switch inductively without failing from overvoltage or excessive energy during turnoff. It's a realistic test because inverters, motor drives, and welders all involve highly inductive loads. What the number means. For the FGH40T120SMD, ILM equal 160 amps means that at room temperature, 25 degrees Celsius case, the device can safely handle a single clamped inductive pulse of 160 amps without damage when switched off under the specified conditions. That's not a continuous current. It's a momentary pulse test that checks ruggedness and avalanche capability. 4. Why 100% of the parts tested matters. Semiconductor manufacturers don't always test every single chip for every parameter. That would be too slow and costly. Some parameters are tested only on sample batches. But here, Fairchild guarantees that every single device leaving the factory is individually tested for ILM performance. So every one of these IGBTs has actually survived that 160 amp inductive switching test before it's shipped. This ensures that the device isn't just theoretically rated, but physically verified to withstand that stress. It's a mark of reliability, especially important for industrial and high-power applications where failure can be catastrophic. In summary, ILM means clamped inductive load current, a measure of how much current the IGBT can safely handle during inductive turnoff. The 1 refers to the specific test setup note in the datasheet. The phrase 100% of parts tested for ILM1 means every IGBT sold has passed that high current stress test, proving it can safely turn off a 160 amp inductive pulse at 600 volts. Beautiful. That's another excellent foundational question. The phrase high input impedance appears often in datasheets, but it's easy to overlook what it really means and why it's one of the main reasons IGBTs and MOSFETs replaced older transistor types. Let's explain it simply and clearly. 1. What input impedance means. Every transistor has an input and an output. The input impedance tells us how much current the input needs in order to control the output. If the input impedance is low, the input draws a lot of current, like a low-value resistor. If it's high, it draws almost no current, more like an open circuit. So a high input impedance device is one that you can control just by applying voltage, not by feeding it current. HRNA 2, the difference between old and new transistor types. Older bipolar transistors, BJTs, are current-controlled devices. To make them conduct, you must inject a base current that's roughly 1/10 of the collector current. For example, if you want 10 amps through the collector, you might need 1 amp into the base, and that current must keep flowing the whole time the transistor is on. That means the driving circuit has to supply a lot of power just to operate the transistor. By contrast, MOSFETs and IGBTs are voltage-controlled devices. Their input, the gate, is separated from the semiconductor by a thin layer of insulating oxide. That oxide makes the gate behave almost like a capacitor. To change its state, you only need to charge or discharge that tiny capacitance. Once the gate has the proper voltage on it, no continuous current flows into it. In other words, it's like controlling a water valve with an electric field instead of constantly pushing current through it. 3. Why this is good. High input impedance brings several major benefits. 1. Low control power. The driving circuit consumes almost no steady current. You just need short pulses of current to charge and discharge the gate capacitance when switching. That means the gate driver can be small and efficient. 2. Simple control electronics. Because the gate responds to voltage, not current, it's easy to drive directly from logic level or microcontroller circuits through a driver chip. 3. Electrical isolation between control and power. The gate circuit is largely isolated from the high power current path. That makes the device easier to protect and monitor. 4. Fast switching capability. The gate responds quickly to voltage changes, so the device can turn on and off in tens of nanoseconds. 4. The practical picture. In an IGBT like the FGH40T120SMD, the gate acts exactly this way. When you apply about 15 volts to it, the internal channel forms and the main collector emitter current starts flowing. When you remove that voltage, the channel collapses and the current stops. During steady on or off states, the gate draws almost no current, only tiny leakage on the order of nanoamps. That's what high input impedance means here. The device doesn't need a strong, continuous drive current to stay on. Con, or 5, why it's especially valuable for power electronics. In large power converters, dozens or even hundreds of transistors may be switching at high frequency. If each one required large base current like a bipolar transistor, the drive circuitry would be huge and inefficient. Because modern IGBTs have high input impedance, all that control can be done with small, lightweight gate drivers that only provide quick charge pulses. That's one of the main reasons why modern power electronics, from solar inverters to electric cars, use MOSFETs and IGBTs instead of BJTs. Absolutely. That's an excellent and very insightful question. You're right. Deep down, an IGBT does conduct current through a bipolar transistor path, and that bipolar part does, by its nature, require charge carriers to stay on. So, how can the IGBT still be called a high input impedance device? Let's unpack that step by step. 1. The IGBT really is a hybrid mode. Inside an IGBT, you can think of two sections working together. The upper part, near the gate, looks like a MOSFET. It has the same insulated gate structure. The lower part, near the collector, acts like a bipolar transistor. The MOSFET section controls the flow of electrons into the base of that internal bipolar transistor. When the gate is given a positive voltage, the MOSFET channel opens and injects electrons into the base region of the bipolar part. That base region then turns on the bipolar transistor, and heavy current begins flowing from collector to emitter. That's the main power path. 2. Where the control signal ends. Now, notice the crucial point. The control current needed for the bipolar transistor does not come from the external gate drive. It's supplied internally by the MOSFET channel using carriers already inside the device. From outside, you're only charging the gate capacitance of the MOSFET. That's a purely capacitive action. Once the gate voltage is in place, no steady current flows from your driver circuit into the gate. So, even though the internal bipolar part needs charge carriers, they are generated inside the chip, not drawn as a continuous base current from your control circuit. That's why the input impedance, as seen from the gate, is still very high. 3. The hidden current. Charge carriers inside it. You're correct, though, that inside the IGBT, current does flow to keep the bipolar section saturated. That's why, during conduction, there's stored charge in the drift region, a mixture of electrons and holes. This stored charge is what makes IGBTs slightly slower to turn off than MOSFETs. But the key distinction is that this internal charge doesn't come from the gate terminal. It's created by internal injection mechanisms controlled by the gate voltage. You could say the gate commands the bipolar transistor rather than feeding it. 4. Why it's still called high input impedance. When datasheets say an IGBT has high input impedance, they're talking about what you, the designer, see at the gate pins. From your perspective, the gate behaves just like a MOSFET gate. It's insulated and draws practically no DC current. You only need brief pulses of current when switching to charge or discharge the gate's capacitance. For example, in the FGH40T120SMD, the total gate charge is around 370 nanocoulombs. At 20 kilohertz switching frequency, that translates to an average gate current of only about 7 milliamps, far lower than the amperes of base current a comparable bipolar transistor would need. That's why the term high input impedance is accurate. The control interface is voltage driven and consumes almost no steady power, even though the conduction path inside is bipolar in nature. 5. A simple analogy. Think of it like a hydraulic system. The MOSFET gate is the valve handle you turn. It doesn't need much effort. The bipolar transistor is the hydraulic piston that actually moves the heavy load powered by pressure from inside the system. You only command the motion. You don't provide the mechanical force yourself. That's exactly what happens in an IGBT. The MOS gate gives the command, and the internal bipolar section supplies the muscle. So, in summary, yes, the IGBT's main current is bipolar, and yes, that path needs charge carriers to stay on. But the control signal that regulates it is still purely voltage-based because the insulated gate isolates you from that internal current flow. That's why the device can combine MOSFET-like control with BJT-like conduction, and why its input impedance remains high. That's a fantastic question, and it shows you're really thinking like a power engineer now. Let's explore this carefully and realistically, because it gets right to the heart of what makes IGBTs such a sophisticated piece of technology. 1. In theory versus in practice. When the datasheet says the IGBT has turn-on delay times or rise times of a few dozen nanoseconds, that's describing the electrical transition inside the device, under controlled test conditions, usually at around 600 volts, 40 amps, and with a specific gate resistor. But that doesn't mean the device instantly goes from conducting 40 amps at nearly 0 volts to blocking a kilovolt with zero current in just a few nanoseconds. The real switching process is spread over several stages, each lasting tens to hundreds of nanoseconds, depending on conditions. 2. What actually happens during turn-on? When you drive the gate positive, the MOS channel forms almost instantly. That allows electrons to flow into the base region of the internal bipolar transistor, which begins to conduct. Current ramps up as carriers fill the drift region. The external circuit sees the voltage across the device fall from the DC bus voltage, maybe 600 or 800 volts, down toward a couple of volts as current rises. This transition can take perhaps 50 to 100 nanoseconds in a well-tuned system. So yes, the IGBT can move from blocking hundreds of volts to fully conducting in that kind of time frame, but it's not an ideal step. It's a fast but controlled ramp shaped by the gate resistor, the driver strength, and the circuit's inductances. 3. During turnoff. Turnoff is trickier. When you pull the gate voltage back down, the MOS channel closes quickly, cutting off the supply of new electrons. However, the bipolar region still contains a cloud of stored charge, electrons, and holes left over from conduction. Those carriers have to recombine or be swept out before the current can drop to zero. This tail of charge is what limits IGBT turnoff speed. Depending on the design, the fall time may be only a few tens of nanoseconds, but the tail current can last another 100 or 2. The field stop structure helps reduce this by giving carriers a region to recombine efficiently, which is why modern trench field stop IGBTs can switch in under half a microsecond, even at high voltage. 4. What tens of nanoseconds really means. In the Fairchild FGH40T120SMD datasheet, typical figures are turn-on delay, about 40 nanoseconds, rise time, about 47 nanoseconds, turn-off delay, about 475 nanoseconds, fall time, about 10 nanoseconds. So yes, the edges of the switching waveforms are measured in tens of nanoseconds, especially the voltage transitions. But the full on-to-off process, including charge storage, is more like a few hundred nanoseconds. At a switching frequency of, say, 20 kilohertz, that's perfectly fine. Each cycle is 50 microseconds long, and spending half a microsecond switching is only about 1% of the cycle. 5. How it's possible physically. The key to achieving this speed while handling hundreds of volts is the device's geometry and materials. The thin drift region, thanks to the field stop layer, keeps carrier transit time short. The trench gate controls current vertically through the chip, minimizing delay. The gate driver provides strong current pulses, often several amps, to charge and discharge the gate quickly. The external circuit includes snubbers and freewheel diodes to tame voltage spikes from inductance. With those design elements, an IGBT can switch a kilovolt and dozens of amps in a few tens of nanoseconds of edge time without exceeding its safe limits. 6. Real-world example. In a typical inverter leg running at 600 volts, the voltage across the IGBT might fall from 600 volts to 2 volts in about 50 nanoseconds, while current rises from 0 to 40 amps. That corresponds to a voltage slew rate of around 12 volts per nanosecond and an energy loss of only a few millijoules per transition, consistent with the datasheet's switching energy numbers. That's fast enough for 20 to 50 kilohertz operation in power systems, which is the normal working range for devices like this. In 7. In summary, so yes, modern field stop trench IGBTs really can transition between fully off and fully on states within tens to a few hundred nanoseconds, even at hundreds or 1,000 volts. The key is that it's a controlled transition, not an instantaneous jump. The gate driver, device physics, and circuit design all shape the speed to balance switching losses, voltage spikes, and electromagnetic noise.
We will move on to the next section shortly, but before that, I want to share something that might be very useful for you. In fact, I want to quickly endorse one VPN service. Here we go. Even if you have nothing to hide, you probably wouldn't like the idea of being watched or tracked. So the main reason why internet users choose VPN services is online privacy and security, and unlocking global content. When you browse the internet using a VPN, your communications are encrypted, so with a good, reputable, paid VPN, you can be pretty confident that your search history will not be public, and you'll be able to access the geo-restricted content wherever you are, as it will seem like you're browsing from elsewhere, especially useful while traveling. And your ISP hackers and other third parties will not be able to see which websites you visit or interfere with your online activities. Another great thing about using a VPN is that you can take advantage of discounts on stuff like flights and bookings because the booking services often change prices based on your location, and VPN makes it seem you are browsing from elsewhere. A good paid VPN allows you to connect to hundreds of remote servers in different locations. So, one VPN service I endorse is NordVPN. I see reputable creators taking them as sponsors, so we can rest assured about their integrity. NordVPN has been delivering since 2012. It is developed by Nord Security, a cybersecurity company incorporated in Amsterdam, with operations based in Panama for privacy reasons. Use my link in the description and pin comment to take advantage of their currently active promotional offers and promo codes. There I've put the up-to-date details on what their generous offers are and what the promo codes do. Alright, and with that out of the way, we're pretty close to getting to the next section of the video. I've also prepared a video for you that talks more about that, as well as solutions to challenges like online security, financial progress, and additional creativity. There, we'll explore these topics with respect and care for you. I warmly invite you to watch this video when you get a chance. Either way, your support is the current that powers this channel. And now back to the show.
Short answer up front. For a trench field stop IGBT like the FGH40T120SMD, practical hard switching at high voltages, hundreds of volts up to 1 kilovolts, is normally limited to the low tens of kilohertz in real, robust designs. With aggressive cooling and lower currents, you can push toward the 30 to 50 kilohertz range, but beyond 50 kilohertz, hard switching becomes increasingly impractical. Switching losses, diode recovery, DV, DTDI, DT stress, and EMI become the dominant problems, and you normally switch to soft switching topologies or different devices. Below I show why, with concrete numbers using the datasheet switching energies and gate charge so you can see the trade-offs. How to think about the limit 1. Every turn-on turn-off cycle burns energy inside the device. The datasheet gives typical switching energy numbers for a test condition. The per cycle energy multiplied by switching frequency equals switching power loss. When switching power plus conduction power exceeds what your cooling heatsink can remove, that frequency is too high. 2. You also need to account for gate driving energy, diode reverse recovery losses, extra losses at higher junction temperature, and practical limits from stray inductance, which creates unacceptable voltage overshoot and EMI. Concrete datasheet numbers, used below, Total switching energy, ET VCC equals 600 volts, IC equals 40A, RG equals 10 mopes, TC equals 25 degrees Celsius, 3.8 millijoules per switching event. That is 0.0038 joules per cycle. ET is at high temperature, TC equals 175 degrees Celsius, 5.9 millijoules, 0.059 J. Gate charge QG370NC equals 37010 Mars C. Gate drive voltage V drive of 15 volts, typical. Diode reverse recovery charge QRR example, 234 NC at 25 degrees Celsius, much larger at high T. Key formulae, switching power ETS F watts. Gate driver power QG's V drive F watts. Reverse recovery energy rough estimate, QRR cons V bus per event. Examples, step-by-step arithmetic shown. 1. If ETS equals 0.038 J per cycle and you pick F equals 20,000 Hz, 20 kilohertz, switching power equals ETS tax F equals 0.038 J 20,000 F minus C equals 76 just joule per second 76 W. So the device would dissipate Pasha's 76 watts just from switching losses, ignoring conduction losses. That's reasonable with a good heatsink heat slug. 2. Gate driver power at 20 kilohertz. Energy per gate cycle, QG times V drive equal 370 times 10 minus C, 15 volts equal 5.5 times 10 minus C J, 5.55 microjoules. Gate driver power, 5.55 10 cis J times 20 ZNS equals 0.111 Joule per sec equals 0.111 W. So gate drive dissipation is negligible compared with switching energy. 3. If you want to budget, say 200 watt maximum switching dissipation. Max frequency PBA budget ETS equals 200 watts 0.038 J equals 52.631 Hz, 52.6 kilohertz at 25 degrees Celsius numbers. But remember two important caveats. At elevated temperature, ETS grows. Datasheet ETS equals 0.059 J at 175 degrees Celsius. Using that number, the same 200 watt of budget gives F equals 200 by 0.059 equals 3,398 Hz, 33.9 kilohertz. The datasheet ETS figures were measured at VCC equals 600 volts and certain currents. If you operate at 1 kV or at higher currents, switching energy typically increases, roughly proportional to the product of voltage and charge time, so the maximum frequency must be reduced accordingly. Reverse recovery and diode effects. The built-in diode has QRR, e.g. 234 NC at 25 degrees Celsius. Reverse recovery energy per event is roughly QRR as V-bus. For V-bus equals 600 volts, ERR star 234 and 10 C, 600 volt 1.44410 NA, J equals 0.4 majars. Small compared to ETS. At high temperature, QRR can be much larger. Datasheet shows QRR up to 1800 NCs at 175 degrees Celsius, which can add 1.08 millijoules per event at 600 volts, non-negligible. At 1 kilovolts, these numbers scale up and add more to switching loss. Other practical limits that kill high-frequency hard switching. Thermal limits and local hotspots. Even if average power looks okay on paper, pulsed heating and finite thermal impedance can create local temperature spikes. Voltage overshoot due to stray inductance. High DIT during fast turnoff creates LDT spikes that can exceed VCC's max and damage the device unless snubbers or RC damping networks are used. The faster you try to switch, the bigger the spike for the same circuit inductance. EMI and layout constraints. Faster edges produce more radiated and conducted EMI, often requiring heavy filtering that itself imposes loss or size penalties. Safe operating area, SOA, and avalanche margins. At high voltage and current, you must keep within the SOA for the pulse duration. Fast switching shortens time in SOA, but still exposes device to high EF and stresses. Gate drive current peaks. You said you have a suitable driver. That's necessary. To get tens of NS edges, you will often need several amps of peak gate current to charge-discharge gate capacitance quickly. Putting it into practical design guidance, for heavy switching at hundreds of volts and tens of amps, design for up to 20 kilohertz of hard switching for a robust conservative product with comfortable margins. That is common in industrial inverters. If you reduce current or voltage, improve cooling, and accept tighter margins, you can push into 30 to 50 kilohertz. Expect larger switching loss, more severe diode recovery, and more challenging layout EMI. At or above 50 kilohertz, hard switching at 600 to 1200 volts and heavy currents is usually not cost-effective. Designers typically move to soft switching techniques, LLC, resonant, ZVS, ZCS, or different semiconductor families, wide bandgap devices like SiC MOSFETs, which have much lower switching energy at high frequency. if they need very high switching frequency at high voltage. Excellent. That's an important label to understand because it doesn't describe the electrical behavior of the part, but rather its environmental and safety compliance. Let's go over it in plain, clear terms. 1. What RoHS stands for. RoHS means Restriction of Hazardous Substances. It's a directive created by the European Union, officially called Directive 2011/65/EU, and later updates such as 2050/863. Its purpose is to reduce the use of certain toxic materials in electrical and electronic equipment. So when a device or component says RoHS compliant, it means it does not contain those restricted hazardous substances beyond very small allowed limits. 2. Which substances are restricted? The main substances RoHS limits are 1. Lead, Pb, traditionally used in solder and component finishes. 2. Mercury, Hg, used in switches, relays, and some lamps. 3. Cadmium, Cd, used in contacts, pigments, and batteries. 4. Hexavalent chromium, Cr3, used for metal plating and corrosion protection. 5. Polybrominated biphenyls, PBB, flame retardants used in plastics. 6. Polybrominated diphenyl ethers, PBDE, also flame retardants. 7. And later additions, 4 specific phthalates, DEHP, BBP, BP, DIBP, used as plasticizers. Each is limited to concentrations of about 0.1% 1000 ppm in any homogeneous material, except cadmium, which is limited to 0.01% 100 ppm. 3. Why RoHS exists. Electronics often end up in landfills at the end of their life. Without restrictions, toxic materials could leach out or be released into the environment when burned or recycled. RoHS ensures that new electronic products are safer to handle, recycle, and dispose of, protecting both people and the environment. It's part of a larger framework in Europe that also includes WEE, Waste Electrical and Electronic Equipment, which deals with how products are collected and recycled. 4. What it means for a component like the FGH40T120SMD. When the datasheet lists RoHS compliant, it means the semiconductor package, leads, and solder plating do not contain lead or other restricted substances beyond the permitted trace limits. The manufacturing process complies with the RoHS directive. You can safely use the part in equipment that will be sold in markets where RoHS compliance is required, the EU and most other regions that have adopted similar regulations. Practically, it also means that the leads are lead-free plated, often tin, nickel, or other compliant finishes. The soldering process may use higher temperature lead-free solders, around 260 degrees Celsius reflow temperatures. 5. Why it's a feature. Manufacturers highlight RoHS compliance as a feature because it signals environmental responsibility, regulatory compliance for global markets, and reduced risk of using obsolete restricted materials. For engineers and designers, it simply means you can use the component in any modern product without violating environmental regulations. HAMR 6. Summary. So when you read RoHS compliant in the datasheet, think, open quote, this part is free of lead and other toxic substances, safe for modern manufacturing, and legally approved for use in environmentally regulated markets. Close quote. It's about environmental safety, not performance, but it's essential for any commercial or exported design.
Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this offer as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermalau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel. Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this offer as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermalau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel. Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this software as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermalau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel.